Why do we bother being so careful to design systems to have constitutive laws that are linear? It's a reasonable question, particularly considering that we just learned in Lecture 4 that Euler integration allows us to approximate solutions to ordinary differential equations whether they are linear or not, so long as dt is small enough. Maybe having an exact analytical solution isn't worth the trouble. The real value of linear constitutive laws comes from the fact that we get to use what is called the principle of superposition. The key thing about linear constitutive laws and the resulting linear ODEs is that if I give you two solutions, regardless of how I obtain them, you can get a whole bunch of potential solutions from those two. We know that Euler integration requires having an initial condition to get started, but superposition allows us to solve for everything we need without worrying about the initial condition until the very end, after we have done most of the calculations. This ends up being a really powerful idea. Starting with our favorite example, the spring damper system, with k equals 2 and b equals 1, we know that we get a differential equation of the form x dot of t is equal to minus k over b x of t. And to remind ourselves, we'll say that k equals 2 and b equals 1. How can we even have two solutions? Well, every initial condition gives us a different time evolution, so every initial condition corresponds to a different solution to the differential equation. In this case, we might have x1 at time 0 is equal to 1, and x2 at time 0 is equal to minus 2. From this, using the fact that the solution for each initial condition is exponential, we can conclude that x1 of t is equal to e to the minus 2t. And x2 of t is equal to minus 2 e to the minus 2t. x1 is an exponential and x2 is an exponential. Note that in this expression of the solutions, x2 is multiplied by negative 2 because the initial condition for x2 is negative 2. Now let's assume that we have two numbers, alpha and beta. Now let's assume that alpha and beta are numbers. That is, they are numbers like 1 or 1/2 or pi, or later we will even allow these numbers to be imaginary numbers. Then the principle of superposition tells us that x of t equal to x sub 1 plus x sub 2 is a solution as well. It tells us that x of t equal to alpha times x sub 1 is a solution for any choice of the number alpha. Similarly, x of t equal to beta times x sub 2 is a solution for any choice of beta. Combining these into a single expression gives us x of t equal to alpha x sub 1 of t plus beta times x sub 2 of t is always a solution to the differential equation. That means that if I give you two solutions to the differential equation, you can generate a whole bunch of solutions with them. Now let's say that x dot equals a of x. And we have two solutions, x1 of t and x2 of t, both of which solve the differential equation. Now we're going to define x of t is equal to alpha x1 plus beta x2. Now the question is, does x of t solve the differential equation? So we have to look at d dt of x of t, which we know is d dt of this expression, but we know that alpha and beta are both constant, so that's equal to alpha x1 dot plus beta x2 dot. And we know that x1 dot is equal to a times x1, and we know that x2 dot is equal to a times x2. Now if we factor out the a, we get a times alpha x1 plus beta x2, and that of course is just equal to a times x. That means that x really does solve the differential equation. Let's look at our specific example. We have the two solutions I just mentioned. x1 of t is equal to e to the minus 2t, and x2 of t is equal to minus 2 times e to the minus 2t. So that means x of t can be defined by adding those two solutions together. If I then take the derivative of x of t, that means that x dot is equal to minus 2 e to the minus 2t plus 4 e to the minus 2t. But this is equal to minus 2 times e to the minus 2t minus 2 e to the minus 2t, which is equal to minus 2x. So x really does solve the differential equation. We can do the same thing with x of t equal alpha x1 of t and find that this also solves the differential equation. So what should you remember from today? Remember that when you have a linear constitutive law and the resulting linear constant coefficient ordinary differential equation, you get to use solutions you have already computed to find new solutions. Why would you need to do this? You might have already calculated the solution for one initial condition, and then someone tells you that the original initial condition was wrong, and you need to do it again for a new initial condition. For a simple system, you would probably just calculate the whole solution again, but as systems get more complex, if there were thousands or millions of spring damper components all connected together, recomputing the solution might take a very, very long time.